questions do you have? Got a beef over the math center. Oh, why you have a beef?
Hard.
Oh my gosh.
The fraction over the fraction.
That was stupid.
Yeah. AB plus AB plus A is equal to
Yes,
AB.
with the A plus
That was
H stuff, yeah.
Or over H.
Okay. What was wrong with it?
It was just very unexpected.
Yeah.
Just having to expect it right.
Okay.
Yeah,
thug it out.
Yeah, and I told you how to do it. So,
Maybe one of those.
yeah. Hope you had an announcement for them.
Oh yeah. So I have my office hours I'm gonna do is gonna be Wednesdays from 2:30 to 4:30, and then Fridays from 1 to 2. So I'll be in the math center at that classroom to the right, right when you walk in. If nobody's in there, I'll be in there. If not, I'll probably be in the math center at the table or the math suite, I guess.
Yeah.
And I'll start those this week and be there every week. So you guys can help with it.
I wrote those down already, didn't I hope?
Yes.
All right, so her office hours are not in the math center. It's in the math suite where my office is. So it's in Schilling 203, which is the one that's at the end of the hall on the second floor, that end, all the way at the end. It says math and computer science over the top of it. So she's going to use the classroom. Literally, it's as you walk into the door in the math suite, there's a little classroom off to the right. That's where she'll be. Okay. Math center is one of the 204. But that's math suite. Two different places, but she'll be right there. So you'll be able to find her. Anyway, it's just extra resources. So you've got you've got my office hours, you've got math center hours, and you've got Hope's office hours to get some help. Okay. All right. Anyway, well, let's continue on with what we talked about last time. So what we worked on pretty much all the way through class last time was to get kind of a library of graphs. So just to kind of scroll back up to talk about, look what we talked about last time. We had some of those that were power functions. What we mean by power functions is we have x to some positive integer power. So we graphed a couple of different ones. We did x cubed, we did x to the fourth. I noticed that x cubed, the power was odd, so it did this lower left to upper right idea, versus x to the fourth, we've got an even power, and we have that kind of U-shaped graph. Now, they'll be steeper or flatter, depending on how big your power gets, but odd power functions look a lot like x cubed. Even power functions look a lot like x to the fourth. Okay? So keep those in your mind. And we'll be talking more about those later as we go through the semester as well. We also talked about those reciprocal functions last time. Big thing about the reciprocal functions, what can't you plug into x? 0, right? Because it makes the denominator 0. Notice that where we can't plug in 0, or we can't plug something into the denominator, we get this vertical asymptote piece, right? We see it both in the even power in the denominator and the odd power in the denominator. That doesn't necessarily always happen. We'll talk later when we talk about what we refer to as rational functions, about when we have an asymptote versus when we just have a hole. Okay? But generally speaking, you're going to have some sort of a graph, break in your graph when you've got a 0 in the denominator. But again, notice we have these kind of different shape, or at least different behavior ideas of even power versus odd power. Notice this even powered one, we were above the x-axis the whole time, versus the odd power one, we kind of had a flip-flop idea. We also talked about root functions. The first one was square root. The second one was cube root that we did for examples. Notice that when you have an even root, a square root, a fourth root, a sixth root, you can't put negatives in those. All right? So we only get this kind of half graph, if you will, right? It stops at the origin. Versus when you've got the odd roots, we can go on both sides of the origin in that case. So even root graphs should look like the square root function. Odd root graphs should look like a cube root function. Roughly speaking, we're just trying to get rough ideas of what these things look like, right? The idea behind this is that if you know what a basic shape looks like, then you can start talking about the behavior of those things a little bit more easily. And we'll build on this as we go through the semester. This is not a one and done. I expect you to understand it all right now. Okay. Finally, the last one that you should have an idea for basic shape of is absolute value. And that's that nice little V shape. Okay. All right. So what we're going to concentrate on today is what happens when we start throwing some constants in there. Okay. All right. So we're going to do that. We're going to build on this later. But in particular, let's just start with a couple of these today and see if we can kind of guess what's going on. So this one's got y equals 3 times the square root of x. Oh. If I didn't have that 3 in there, and just had square root of x, I already know what that graph looks like, right? We just talked about that before. As a matter of fact, go back up, it's graphed right there, isn't it? Okay. I'm just going to recopy it down here. We know it goes through the points 0, 0, 1, 1, 4, 2, 9, 3. And again, we've got this graph that looks like this. And again, this is y equals square root of x, right? That's not the graph we're looking at. However, we can go off of this graph to help us get the new one. Okay? So notice that, for example, this first point here is 1, 1, right? That means when we put 1 in for x, we got 1 out for y, right? Okay. Well, notice that would be just this part here, wouldn't it? So if I want 3 times the square root of x, rather than getting 1 out, what would we get out in this case? 3, right? So I would be up here. I can change my color. Oh my heavens. Change the color. Thank you. Good grief. It'd be up here, wouldn't it? Be at the point 1, 3 rather than 1, 1. What about the next one? What's the coordinates of this point right here?
14.
It was 4, 2. Again, that means that when we plugged in 4 for x, we got out 2 for y, right? But what are we going to do with the 2 in this new function? Multiply it by 3, right, on the outside? And so instead of getting 2 out, what do we get? 6. So the point's going to end up being up here at 4, 5, 6, up here, right? Nope, not at 2, though. Here. That makes sense? Finally, this last one over here would have been the point 9, 3. What are we going to get instead? 9, 9, right? Be up here. And now we can kind of get an idea what the graph looks like. Now notice that the basic shape is the same, right? We still kind of started at the origin, We started at the origin, and we're going up and to the right, and it's bent down a little bit, right? It goes up, but not. It's going up, but more slowly as you go to the right. It's just taller, isn't it? Okay. As a matter of fact, how many times taller is it? What did we do to each of the outputs? 3 times, right? Okay, so we call this a vertical stretch. So just to use some of the language that we'll use later on, we would use y equals square root of x as our what we refer to as a base graph. That was what I started with, right? That square root of x that we already knew what the graph looked like. And then the 3 is multiplied on what we refer to as the outside of the function. See what I mean by the outside? The function with square root of x, and the 3 is on the outside of it. That makes sense for outside. Okay, it's on the multiplied on the outside of the function. So the graph of y equals 3 square root of x, oops, I can write, is 3 times as tall as the graph of y equals root x. It's 3 times as tall. The words we typically use by this, or for this, is we say the graph is stretched vertically by a factor of 3. Like I said, we're going to focus more on this later. Right now, we're just kind of dipping our toe in the water, so to speak. We're just trying to introduce what's going on. When you multiply on the outside of a function, it affects the output. It affects the y's, right? Multiplication by that constant gives you a stretch, or we call it compression if it's smaller than 1. I want to introduce this now. We're going to come back to this idea later on because we're going to kind of put a whole bunch of things together in a later section. But right now, I just want to start introducing some of the words. Do we understand how it's making it 3 times as tall? Okay. All right. But notice what we did. We started with a base graph and then used that base graph to help us get a new one. Okay. So looking at this next example, what do you think we might want to use for our base graph? Yeah, the absolute value of x. Good. So let's start with that. The absolute value of x was that V-shaped graph, right? Oof. It's hard for me to draw a straight line. It gets wavy as I go. All right. So this was our base graph. Ignore the negative sign for the time being. We'll fix that in a second. Let's ignore the negative sign because that should remind us of what we just did in the previous example. Is that 1/2 on the inside or on the outside? Outside. On the outside, right? So is it going to affect the inputs or the outputs? Outputs, right? So it's going to affect the y's. And we just said that it's going to multiply all the outputs by that number. So in this case, we're multiplying by 1/2. So is it going to make it taller or is it going to make it shorter? So last one was multiplied by a 3. It was 3 times as big, right? This one's going to be half as big, right? Half as tall. So it's going to compress it. We usually say that's a compression, right? Versus a stretch. But it'll make it half as tall. So let's see if we can figure out some of the points on here. And like I said, we'll do the negative in a second. Let's just ignore the negative for the time being, okay? Let's just do 1/2 absolute value of x. This point right here was an output of 1. So instead of an output of 1, it should be an output of 1/2. Good. This had an output of 2. So it should be at 1. Let's skip over to, just so I don't have to go in half the way in the middle. This had an output of 4. So that'll be an output of 2. That one had an output of 6. So that'll be an output of 3. All right. And it should be mirrored on the other side. If I could draw a straight line, that would be very helpful. So this would just be y equals 1/2. Oops, I wrote square root of x up there before. Why didn't somebody stop me? That was the absolute value of x. Sorry about that. I was thinking about the previous example. What was the absolute value of x? All right. So far, so good. This looks a lot like the previous example, did it? It doesn't, except with a different answer. But what did I tell you to ignore? The negative. Let's not ignore it anymore. Okay? Now, again, let's think about where that negative sign is. Is that negative sign on the inside of the function or is it on the outside of it? Outside. And again, if it's on the outside, it affects the output. Good. So it's going to affect the y's, right? Let's think about how it affects the y's. Well, the negative sign is basically just multiplication by -1, right? So let's work off of the graph we just did. Here was an output of 1, right? Let me change colors again here if I can. This was an output of 1, right? So instead of a positive 1, it'll become -1. This had an output of 2, so instead of positive 2, it'll be negative. Likewise, we'll get a -3, -1 here, oops, not there. -1 here, -2 here, -3 here. Same basic shape, but what did that negative sign do? Flipped it. Good. Okay. So we have two, what we refer to as transformations here. So the base graph was absolute value of x. We've got a vertical compression of a factor of 1/2. It's a compression versus a stretch because it got flatter, not taller, right? Does that make sense? That's why it's the different word. Okay. And then we also, what we refer to as a reflection about the x-axis. Flipped upside. A reflection about the x-axis just means it got flipped upside down. That's how it affects the output, right? Flipping it upside down changes the output, not the input. Yes. So we're going to start with.
Like on a center, is our point
This part?
Yeah.
Oh, no, we're still at the origin. Yeah, so nothing moved off the origin. We'll talk about shifting here in a minute. Other questions on that one? So, constants on the outside either stretch or compress, depending on if it's bigger than 1 or less than 1. The negative will flip it upside down if there is one. So the negative will make a reflection. All right. Let's look at the next example. Notice in this case, rather than multiplying, we are adding, right? But again, is that +1 on the inside or on the outside? Outside. So you'd expect it to affect the output, right? The y, right? It's on the outside, it affects the output. Okay? All right. What do you think I'm going to use for a base graph? The x squared, right? Just use the x squared. That's our base, right? We'll do the base and then we'll do the +1 and see what happens. Okay? X squared is one of those power functions, right? So again, the exponent tells you about, does it go like this or does it go like this, right? Which is it? Is it this way, the first one, or the second one? Yeah, number 1 or number 2? Is it better now or better now, right? Okay, it's the second one, right? They both point up, correct? Okay, so our squaring function, we have 0, 0, 1, 1, 2, 4, 3, 9, 9, and they're both going to point up. All right, so our base graph here, y equals x squared. plus 1 does. So again, you'll put a number into the x squared, you'll square it, and then you will add 1, right? So let's see what happens with the different output. You already told me it was the output, right? Okay, so let's just go on these points that I have identified here. Let's start at 0, 0 here. What was the output here? So it'll be, instead of 0, it'll be 1, right? Here the output originally was 1, so now it'll be 2. Here the output was originally 4, so now it'll be 5. Instead of 9, it'll be 10. Same thing on the other side. What did we end up doing? Just moving it up 1, right? No stretch, no flatten. Just a shift, right? We call that a shift. Okay? All right, so we get what's referred to in this case a vertical shift. Oops. Of 1 unit. In this case, it was upward. How do you think we would get a shift of downward? What do you think we would do? Yeah, subtract something rather than add, right? If we wanted to shift it down, we'd have a subtraction versus an addition. Exactly right. Good. All right, so just to summarize a little bit, multiplication on the outside is a vertical stretch or compression. Addition or subtraction on the outside is a shift up or down. Like I said, later on we're going to put all these things together, but we'll just kind of do a little bit of an introduction so that we can help get some graphing, especially when we do piecewise defined functions here in a minute. Are there any questions on any of those at all? So far, so good? Okay. All right, so switch gears. Well, it seems like switching gears slightly, but we have well, remember, a function is something when you put in 1 input, how many outputs are you allowed to get? 1, just 1 output, right? Put 1 thing in, you get 1 thing out. You can't get more than 1, right? Okay. So if we have a graph of a function, we have a test that we can use to help us determine whether or not that graph actually represents a function, okay? So to give an example here, let's look at this first graph, this circle. What are the coordinates of this point right here that I'm coloring in? That's 0, 2. Down here it's 0, negative 2, right? Now again, remember when we think of graphs of functions, x goes in, y comes out, right? We agree with that? X goes in, y comes out when we think about graphs of functions, okay? How many outputs do you see associated with the input of 0 here? 2, right? I see 2 inputs. So can this be a function? No. Now notice something else. Why did I pick those 2 particular points? Well, if I look at my y-axis here, my y-axis is a vertical line, isn't it? How many times did that vertical line hit that graph? Twice, right? Okay. That's exactly what the vertical line test says. Okay, so we'll write that down. Is your vertical line test. A graph represents a function if and only if every vertical line intersects the graph. Oops. At most once. It may not hit it at all. There may be a gap in the graph; it doesn't hit it at all. But if a vertical line intersects the graph, it can only do it one time. Okay. So let's look at this next example. Well, certainly over here, I'm okay, right? If I draw a vertical line there, that only intersected one time. If I drew one over here, that only intersected one time. But what happens here in the middle? Yeah, it hits it here and here and here, didn't it? Okay, so does that pass the vertical line test? No. So this is not a function. Oops. We found a vertical line that intersects it more than once. That's the important thing. Oh, I guess I should have written it down where I actually had a space for the vertical line test as it goes up at the top. Sorry about that. My apologies. This actually should go down there. All right. So again, if it intersects it only one time, wherever any vertical line that you pick, that makes it a function. So let's look at the next example. The next couple of examples here. Notice the first one, I just have some dots plotted, but do you see any pair of dots that might be on the same vertical line? Yeah, the ones on the left here, right? Notice here, if I take this vertical line right here, that's going to intersect it twice. Maybe a little bit easier to see. The coordinates at this point are -1, -2. Coordinates of that one are 1, 4. So this is not a function. Oops. What about the next one to the right? No. Can you tell me one specific line that's actually on the picture that intersects it more than one time? The y-axis does, right? Okay. So notice what this tells us about a function in particular is it can only have at most one y-intercept. It may not hit the y-axis at all, but if it does, it can only hit it one time. Okay. So this one's not a function. And like I said, one of the reasons why I put this one on here is a function can only have one y-intercept. It may have none, but it can only have one if it has one. Can a function have more than one x-intercept? Can you hit the x-axis a lot of times? Sure you can, right? You can hit it all the time, as many times as you want. You can hit it infinitely many times. With the y-axis, you only get one shot. That's it. Next one, not a function. We got a few problems, right? This one's not a function, but finally, what about the last one? Yeah, it's a function. Good. Basically, I took the same graph and just deleted off the bottom, right? Again, hole in the middle doesn't matter. That's okay. You can have a hole in the middle, all right? The vertical line just says if it intersects, it only can do it one time. It doesn't say it actually has to intersect. It might be none. All right. Last thing in this section, and then we will go on to some other function ideas here today. Let's see if we can get some graphs of piecewise defined functions. They can be a little bit more intimidating, but it's the same kind of ideas. So let's first evaluate the points that I asked you to evaluate on here. So I want to do f of -2 to start with. Remember, we have to decide which piece it goes into, right? You don't plug it into both. Which one's it going to go into? The top piece or the bottom? The top, because why? Is less than 1. Good. So we put it into the top piece and we get out 4, right? So I want f of 4. The top one, the bottom one, right? Because it's greater than 1, so we get 2 times 4, which gives us 8. Those two okay? Perhaps the more difficult one is when you get to that kind of switch over, right? You got to figure out which one it needs to go into. Which one does it go into? The bottom one, because of the equal sign right there, right? Okay. So far, so good? Right. One of the things that this tells us is it tells us some points from the graph. It's one of the reasons why I put it in here, but we'll get the rest of the graph in a second. we put in -2, we're supposed to get out 4. So we get the point -2, 1, 2, 3, 4 is on the graph. We also get that 1, 2 is on the graph. And we get the point 4, 8. 2, 4, 6, 8 should be here. All right, so I know those points are definitely on the graph. Now, it's a little harder to play connect the dots here because I don't know exactly which function is which to start with. We'll get that here in a second. I could plot some more points, but again, the idea here is that the definition actually changes at x equal to 1. Okay? Well, what if that weren't there? Let's look at just x squared. Do we know what x squared looks like? Yeah, we had that before, didn't we? That graph would come down this way, down this way. I could plot some points, but it bottoms out, and then it goes on forever, right? We agree? But do I want that to go on forever in this case? No, I want it to stop, don't I? Where does it need to stop? At 1, right? So I want this to come up and stop at this point. Now notice it says x is less than 1. It's not equal to 1. So notice I put an open circle here to say that it's coming up to 1, but I don't actually hit that part. Does that make sense? Okay. So that's just graphing the x squared part. So notice actually how I started that. I literally drew my graph to start with, right? And then I got rid of the part that I didn't need. And I stopped it like that, didn't I? That was what I did. Okay. I'm going to do the same thing for the other side. If I look at y equals 2x, what kind of a graph is y equals 2x? What kind of a thing do you get? But if I just have y equals 2x, what kind of a thing do you get? A line, isn't it? Yeah, what's its slope? 2, because that's the coefficient on here, right? What's its y-intercept? Where does it cross the y-axis? At 0, right? Okay. Notice that every time it goes, you go right 1, you go up 2, correct? Okay. So if I were just to graph the line, it would look like the whole. This is the whole line, right? That's the whole line, y equals 2x. Do I want the whole line? No. Where does it need to stop?
1, 2.
At 1, 2, right? So I don't want the whole line. I want it to basically start here and go on this way. Notice that one we'd have a filled in circle because we actually have, when we plug in 1, we get out 2 for that part of the graph, right? It's defined for the right-hand side. Notice again, I look at what the graph looked like the whole time and erase the part that I don't need. So the left-hand piece looks like your parabola. The right-hand piece looks like your line. And that's how we're going to graph all of these, looking at individual piece by piece. What questions do you have about that one? Let's see if we can do another one. I know it's a little strange to start with, right? It's a little odd. All right. So let's look at the next one. Again, let's just plug in the values. Oops. This one asks us to do f of -8, f of 0, f of -1. Which piece do you plug it into for -8? The top one, right? So you have 2 cube root of -8. What is the cube root of -8? So it's 2 if it's just a positive 8, so -8 would make it -2, then times 2 gives you -4. And of course I forgot to write my negative sign. Right, cube root of 8 is 2, so cube root of -8 is -2, then multiply by your 2. Which piece do you plug 0 into? Bottom one, and you get -2. Good. Yep, it's just -2. Yep. Which piece do you put in -1? The top one. And what do you get? -1 for the cube root, and then multiply by the 2, so we get -2. Are we okay with where we're putting those in and how we're getting those values? All right. Let's see if we can get a graph now. Kind of the point of these exercises, right? Get a graph. Okay. All right. So if I want to get a graph, let's look at the bottom one first. It'll be a little bit easier, hopefully, to get that graph since we already talked about it. If I ignore the rest of the whole problem except the x squared minus 2, what would you use for your base graph? X squared, right? What does x squared look like? A U shape, right? Okay. What does the -2 do?
Shifts it down.
Yeah, shift it down 2, right? So if I were just worried about x squared minus 2, I would graph a U shape down here, right? Like this, wouldn't I? I can actually hit where I'm supposed to go. I missed here. Try again. Oh, just a drawing fiend today. We agree with that? If I start with my U shape up and just move it down, I could have plotted some points, but I'm literally just trying to get the basic shape. This okay? We okay with that? All right. Now, that's the whole graph. Do I want the whole thing? No. What do I want? Where do I basically, if I'm looking at the bottom one, where do I want that thing to start, if you will? What x value do I want it to start at? Let's start with the x value. What x value do we want to start at? -1, right? It says x is greater than -1. So if I start at -1, do I want -1 into the left or -1 into the right? To the right, right? So I would get rid of this part over here. I'm at -1, which would be right here. Do I want an open circle or a closed circle? Open, right? Because it's not equal to. And I would just use that part. Okay. So notice again, I took the whole graph and then got rid of the part that I didn't want. I knew what x squared minus 2 looks like, but I got rid of the left-hand side. Right? But it still looks like x squared, it just got chopped. Right? You just chop that part off. That makes sense? Okay. What about the top part now? I just didn't save the top part second because I think it's a little bit more, it feels a little bit more complicated because it's a cube root versus an x squared. All right. What does your cube root function look like? Going back to kind of those basic shapes, what did it look like? It looked like an S, right? Like that. All right. Okay. So again, if I did my cube root function, I'm going to draw it off to the side. It would look like that, roughly, something like that. Just, I'm just looking for basic shape, right? I'm not looking for perfection. God knows I can't draw. You've already seen that. Okay? Not looking for perfection. I'm looking for big ideas. Okay? All right. That would be cube root of x. What does the 2 do to it? Does it go up or does it do something else?
It makes it taller.
It makes it taller, right? Vertical stretch, doesn't it? Okay? So it makes it twice as tall. You agree? Okay. So if you did something twice as tall, well, you would have something that looked like, I'm going to draw it in red and then I'm going to erase it. Okay? I don't know if I can get the red to come up. Yeah, sure, that's what I wanted to do. Stop. Why are you... That was That was trippy. Okay, maybe I won't change the color then. Fine, be that way. I don't know why this is even on there. Go away. Nope. Apparently I can't. Nope. Okay. Anyway, it would go up or not. Go up and to the right, right like this, and down and to the right like that. That S shape. It was twice as tall, right? Okay. Do I want the whole thing? No. Where do I need to chop it off at? What X value do we chop it off at? -1, right? I chop, and what, do I want the left-hand side or want the right-hand side? The left-hand side because it's less than, right? So I erase that off of here. I'm going to erase that off of here, supposedly. We're going to start here. We know when we put in -1, we got out -2, and we'll fill in the dot, and then it's just going to go that way. Not looking for perfection. I am looking for basic idea. Okay? If you'd like a little help with the basic idea, especially if you're doing your homework, there is a nice program available online that we can use to help, and that is called Desmos. DESMOS, Desmos.com. There's also an app for the phone. Okay, if you can always download it on the phone as well. We want the graphing calculator. So I'll open the graphing calculator here. We've got lots of different things, but we want the graphing calculator. So notice we had x squared minus 2. If you want the exponent, just use the caret, shift 6. There's your x squared minus 2. All right? But here's even something nicer. Let me go back up here to the front. If I use braces in front and give it x is greater than -1, which is what we had, right? See what I graphed? Okay. If you want to make sure you've got the right thing, you can put parentheses around the whole thing, make sure it applies to it. But notice I just got x is greater than -1 as that piece. I can do the same thing for the cube root. If I had x is less than or equal to, and literally just type in you type in less than and then hit equals, it'll put the less than or equal to sign there for you. I want cube root of x. Cube root I can do as a fractional power, 1/3 power. There we go. And put it in there. Okay. Oh, I did 2. It was 2 times. It wasn't. Sorry. That was my problem. 2 times. There it is. And now it should look like what we graphed, roughly. Again, rough shape. That's all I'm caring about. I'm not looking for basic. But this will give you an idea if you've got it going right for practice. Okay. Questions on that one at all? I'll leave the last one's a 3-parter. I'll leave it for you for practice. I want to start the next section here briefly. I'll leave that one for practice for you. It's the same idea. Just break it into pieces. So try that for next time. All right, so we're going to start the next section up here, section 2.3. Still talking about functions, but basically, again, it's just illustrating what we would like to use graphs for. So what we're going to do here for the first couple of examples is just read off the graph domain and range and whether or not it's a function. So you should be able to tell me the first answer. You can get one.
I have 2 classes.
All right. So let's look at the first one. The first question you should be able to answer me pretty quickly. Looking at that graph, does that graph represent a function? No, why not? Fails the vertical line test. Where's my pen? There it is. All right, so no, it's not a function. Okay. Doesn't pass the vertical line test. Okay, good. All right, notice I'm using the word relation here. All a relation means is a set of ordered pairs. That's all the word relation means. So any time you draw even any squiggly line on a graph, that represents a relation. You're just talking about all those set of pairs, sets of ordered pairs being included as a single object. That's all we mean by a relation. All right, so this one asks for what's the domain and what's the range? Well, again, domain refers to input. On the graph, what do we associate with the input? The x or the y? The x's, right? The outputs are the y's, correct? So all this problem is asking you is to look at the graph, ignore the y, and just look at the x's. What x's do you see this graph running between? 0 and 6. So the domain is going to be 0 to 6. And we actually hit x equal to 0 and actually hit x equal to 6, right? So do you think we would use a parenthesis or a bracket? Brackets, good. Again, how far left, how far right? We're just looking for the x values that get hit. Ignore the y's. What do you think we're going to do for the range? Yeah, just the y's and ignore the x's. What's the lowest y that you see? What's the highest y that you see? 3. So what do you think the range is going to be? -7 to 3. And again, we'll use brackets. That's all we have to do to read it off the graph. That's pretty straightforward, isn't it? Okay. So let's look at the next one. First question. Is it a function? Yes. Because why?
No more than one y intercept.
So we got no more than one y intercept. That's one vertical line. But if we use any vertical line, it only hits it once, right? Or not at all if we go too far to the left or right. But in particular, it's a yes. It passes the vertical line test in this case. If I could spell the word line, that would be helpful. Okay. All right. For domain and range again. -4 to +4 for the domain. Again, ignore the y's, just look at the x's, right? We see the graph passing through all the way from -4 to 4. Do we include it or not? Yep. So we'll have -4 to 4 in brackets. And again, for the range, we look at the y's. Lowest y is -2. Highest y is 10. So our range is -2 to 10. That's what you need to do for range. Domain and range off a graph. All right. So we'll finish up this handout next time. I think we'll also have a quiz next time over the first couple of sections. Okay, so we'll do a quiz on Wednesday at the end, a few questions over 2.1 and 2.2. Okay. Other than that, I'll see you on Wednesday. Have a good one.